What's the deal with cobordisms? Well, what even is a cobordism? Cobordism is a manifold W whose boundary can be split into two parts. So we have the boundary of W is the disjoint union of two other manifolds, say M and N. In this case, we have M is a couple of circles and N is just one circle. Now we can change our point of reference on this and say that W is a cobordism between manifolds M and N. So if M and N are the boundary, then we say that W is the coboundary, hence cobordism. So we say that M and N are cobordant if there exists some cobordism between them. Logical question is, can we sort manifolds into cobordism classes? That is, manifolds modulo the relation that they are cobordant. Well, for that to be true, we need this to be an equivalence relation, which means there are three things to check. First off, reflexivity. Is a manifold cobordant with itself? Well, yeah, that's pretty easy. We just take the cobordism as the manifold cross an interval. So, like this cylinder here, we can see that its boundary is just two copies of the manifold. Okay, next is symmetry. That is, if M is cobordant to N, is N cobordant to M? Well, again, yes. And we just take the same cobordism between them and use the fact that the disjoint union operation is abelian. We can think of this as taking this cobordism here and just kind of flipping it on its head. Okay, finally we have transitivity. If we have a cobordism between manifold M and M prime, and then another different cobordism between M prime and M double prime, is there a cobordism between M and M double prime? You can see in this picture, again, yes. You just take these two cobordisms and stick them together. Now, there is actually something to check here, unlike the other two. This is non-trivial. We need that this interpolating critter here has to be a manifold. And in particular, it needs to be smooth at this boundary between the cobordisms. So the question is, can we always glue together the cobordisms in a way that this is still smooth? And the answer is yes, which is a result from differential topology that I'm going to black box. Suffice to say, manifolds can be organized into well-defined cobordism classes. So now let's endow a set of cobordism classes with a bunch of extra structures. First up is a group structure, where we're going to take the addition operation to be disjoint union of manifolds. So we need to actually check that this is well defined as an operation on cobordism classes. So translated, that means that if we have a cobordism between a manifold M and a manifold N, and then another one between M prime and N prime, can we get a cobordism between the disjoint union of M and M prime and a disjoint union of N and N prime? And as you can see here, yeah, you can. You just stand them up next to each other. So we have a group structure. And in fact, it's abelian, just owing to the fact that disjoint union is an abelian operation. Now, one interesting thing about this is every manifold added to itself is actually equal to 0 as a cobordism class. To see this, take this cobordism of a manifold to itself, and we can look at this from a different perspective. Let's just take this bottom part and twist it up to the top. So we have this sort of, in this case, this is a sort of horseshoe thing. So instead of thinking of it as a cobordism from M to itself, we can think of it as a cobordism from the disjoint union of M with itself and, well, nothing. Empty set, 0. So they add up to 0. Which means if you so desired, you could consider this group to actually be a vector space over the field of two elements, if you want. So that means we have a well-defined cobordism group for every dimension n, consisting of n-dimensional manifolds. And let's stick them all into one big structure. that contains, every cobordism group for every n. And to intertwine these together, we're going to use a ring structure. And that ring structure is going to be given by a multiplication operation of Cartesian product. So we have to check the same thing we do up here, that Cartesian product is actually well defined up to Cobordism classes. But suffice to say, it is, and in fact, we get this graded ring called the Cobordism ring, graded by dimension of manifolds. So to give you all a taste of this and some sort of sense of how these cobordisms tick, I'm going to run through a couple examples. So first is dimension zero manifolds. Every closed dimension zero manifold is just a bunch of points. So for example, over here we have one manifold, that's just 4 points. Over here we have another, in this case it's only just 3. And a cobordism between them consists of a compact one-dimensional manifold with boundary. Well, every one of those is just a bunch of intervals, and each interval just has 2 points. So the cobordism has to be essentially a bunch of these little strings connecting the points. So for example, we have one string stretching between the manifolds and a couple of strings connecting within each manifold. But then there's this last point. We look at the string coming off here and just there's nowhere to go. There's no other points left. Just look how confused he is, the poor little guy. So this means that these two manifolds are in the same cobordism class if they have the same parity, right? So this is an even number of points, so we get a 0. This is an odd number of points, so we get a 1. And both of these live in the cobordism group of 0 manifolds, which is just Z2. Okay, let's try 1D next. So every closed one manifold is just a bunch of circles, so a disjoint union of a bunch of circles. And in particular, each circle is the boundary of a disk. In particular, that gives us a cobordism from the circle to zilch, nothing. So the cobordism class of a circle must be 0, and thus every closed one manifold has the same cobordism class as 0, which means that the cobordism group is the trivial group. Next we have dimension 2, and in this case, the cobordism group of dimension 2 is, again, just Z2. But for this one, it's the first case where this isn't really immediate. There's some work we have to do to show this. And we're going to do this using the surface classification theorem, which says that every surface is homeomorphic to a bunch of copies of RP2 connected summed together. So RP2 is this bowl here, this bowl thing, and on its boundary circle it has 2 points, and we're identifying the edges connecting those points in the orientations of the arrows given here. To get the connected sum of a couple of these, we cut a little disk outside of each bowl and replace those with a tunnel. So the surface classification says that every surface can be jiggled around to look like something of this form. Now I claim that it suffices to show 2 facts. First, RP2 itself is not the boundary of anything, which means that it is non-trivial in the cobordism group. Second, RP2 connected sum RP2 is a boundary of something, which means it has to be trivial in the cobordism group. Because if that's the case, then when we look at the cobordism group of this connected sum, we can just cancel out any pair of these RP2s. There's some work to do to show that, but thus the cobordism class of a surface is determined by the parity of the number of constituent RP2s. Okay, let's show this first one. We work to find a contradiction. Suppose that there was a free manifold M whose boundary was RP2. We can turn M into a manifold without boundary by just taking 2 copies of itself and gluing them together along the boundary, where we glue them together using the identity map. So we're going to call the boundary that we're going to call the manifold that we get 2M. Next, we use the Euler characteristic and a Meyer-Vittorius argument. So if we take the Euler characteristic of this guy, that's the sum of the Euler characteristics of its constituent parts, which is 1 for each copy of M, minus that of their intersection, which in this construction is just the boundary of M. However, 2M is a three-dimensional, in particular odd-dimensional manifold without boundary, which means it has to have zero Euler characteristic. So we get a formula for the Euler characteristic of the boundary of a free manifold. It's just twice that of the manifold itself. However, we know already that the characteristic for RP2 is just 1, and thus we have our contradiction. This is an even number, this is an odd number, hence RP2 can never be a boundary of a free manifold. Next, we show the connected sum of two copies of RP2 is a boundary via proof by pretty picture. Okay, so we have the connected sum of two copies of RP2. And I'm going to push these around until they make a shape where we can see that it's the boundary more easily. So first step, let's widen out this tunnel. And at the same time, we're gonna push these 2 points together into a single point. And what we're gonna get is this sort of bean-shaped guy. And the top of this, the boundary is going to look like an infinity symbol, where this side has a couple pink parts and this side has a couple yellow parts. Next step, we take this point in the center and we're going to cut it apart into 2 points in a different way than we had before. It's still kosher. And our resulting thing is going to be this bowl, whose edge consists of both pink edges and both yellow edges. And next, we pinch together this bowl, but in a different way. We pinch together the 2 points, these 2 points here, and get another bean shape. But this time, the boundary is an infinity symbol, but each lobe has one pink and one yellow thing. Finally, we cut apart this point and pull it apart in another way to separate the two lobes of the infinity sign. And we end up getting, if we flatten it out and everything, we get a cylinder, where the boundary of one end of the cylinder consists of, yellow going down, pink going up. On the other edge, you have yellow going up and pink going down. So it's a cylinder where the two edges, the two circles on the edge, are identified by an inversion. In other words, it is a Klein bottle. Now, the reason why I went through all of this is because in this shape, the Klein bottle is easy to see. It's easy to see that it's a boundary, right? We just take the cylinder and we just fill it in. And then the discs on the boundary of this guy identify still by an inversion. So the boundary of this manifold here is just a connected sum of two copies of RP2. Hence, we have shown that the cobordism group in 2 dimensions is Z2. So we have these cobordism groups, and great, they're wonderful. The only issue is they're just kind of floating off in space. Like we abstractly got them from just considerations of all possible manifolds. But it'd be much more useful to us if we could somehow attach these cobordism groups, to a space. So that's why we introduced the concept of a cobordism over a space X. So we modified a definition as such. Instead of just manifolds, we're going to consider pairs of manifolds and maps from manifolds to X. So we have M and a map F down into X. And then we're going to say two pairs, M comma F and then N comma G, are going to be cobordant if not only are M and N cobordant, through some cobordism W, but also that W maps down to X in a way that on one side restricts to F and on the other side restricts to G. So doing this gives us a map from topological spaces to groups, or equivalently, we're assigning groups to a given topological space. And this assignment has, a couple of really nice properties. First off, it's a functor. So what that means is, for every cobordism over X and a morphism from X to Y, or homeomorphism, then we should get a cobordism over Y too. And we get that just by stacking it. So we have a map from X to Y here, and this basically the map W factors through X into Y. We get a cobordism over Y. Great. Secondly, it's actually a homotopy invariant of the base space X. So these two properties together combine to say that these cobordism groups over X, they're a good algebraic topology invariant. They tell us stuff about the space X. Now let's get a better sense of what these actually are. So simple case, right? Let's just take X to be a point. Well, in that case, the condition that F and G are cobordant through this bigger map F, that condition is trivially satisfied. So the only condition is that M and N are cobordant. Hence, the groups over a point are just the normal cobordism groups. And in fact, by introducing a space X, we make the groups bigger. Cobordism groups over X is always bigger than those over a point because we have extra conditions applied to our maps F and G. And in fact, if we organize these groups into a ring, like a cobordism ring over X, then this ring is a module over the ring of a point, which is just the normal cobordism ring. Now, what's so remarkable about these cobordism groups is that they actually form a generalized homology theory. Now, what does that mean? It means it satisfies all of the axioms of homology, or the Eilenberg-Steenrod axioms, most of the axioms. So the first couple, functoriality and homotopy invariance, we already showed. The next couple of exactness and excision, to define properly, I'd have to introduce the notion of a cobordism over a pair, which you can do, but then I'd have to also go into the proof about some long exact sequences and stuff like that. I don't find that these constructions are particularly instructive. And in fact, nobody does it this way because there is a much better way to show it as a homology theory. And that is to manifest these cobordism groups as the homology groups associated to a spectrum. So a spectrum which yields cobordism groups is called the Thom spectrum, and its construction and the proof of all these facts is actually super interesting, but that's a story for another video. Now, I don't want to totally leave you high and dry here, so just to give you a sense of why you might expect this to be a homology theory. Arguably, one of the most important implications of these homology axioms is the suspension isomorphism, which says that the groups in degree n of a space X are isomorphic to the groups in degree n plus 1 of the space, the suspension of X. So what does this look like for cobordisms? Well, we have a cobordism over X, so a map from our cobordism W into X, and then to this we apply our suspension functor. So we get an induced map from the suspension of W to the suspension of X. And this right here is an n plus 1 dimensional cobordism. And one can show that this map actually does induce an isomorphism. Now, you might notice that there's one axiom of homology that's missing from up here, and that's the so-called dimension axiom, which states that the homology of a point is 0. And that explains why this funny word generalized up here. Generalized homology theories don't satisfy the dimension axiom. Because if we remember, the cobordism groups of a point weren't 0, they were the whole cobordism ring, which is actually very complicated, but that's what makes it so fun. So who actually cares about cobordisms? Like, how do these fit into the wider pantheon of mathematics? Well, I'd say that their main application is in constructing manifolds, like this cow here. It's constructed from a series of cobordisms. So first from these 4 circles in the feet, then 2 in the legs, and then to 1 in the neck, and then to 0 to cap it off with a head. And this sort of thing is the core ethos behind a circle of ideas known as surgery theory, which gives a way of constructing manifolds based off of a series of cuts and pastes that are manifested using cobordisms. So for this surgery theory to work great, we need some sort of uniqueness. Basically, that any given cut and paste, the cobordism defining it is unique. And we get this through the so-called H-cobordism theorem. So that states that any cobordism between that is homotopy equivalent to both of its boundary manifolds has to be the trivial cobordism. That is just a manifold across an interval. And this would give us the rigidity we need for surgery theory. So interestingly, as a pretty immediate consequence of this, we can actually get the so-called generalized Poincaré conjecture, which asks that any manifold that is homotopy equivalent to a sphere has to be homeomorphic to a sphere. So you're probably familiar with the dimension-free case, the normal Poincaré conjecture, which was actually one of the Millennium problems. So Smale actually proved the H-cobordism theorem for dimensions greater than 4 back in 1960, and thus the generalized Poincaré theorem. And this work won him a Fields Medal. The reasons why it only works in these dimensions is essentially we need enough degrees of freedom in order to untangle a general H-cobordism back into the trivial cobordism. Now, interestingly, this H-cobordism theorem gives us that manifolds in dimensions greater than 4 are entirely classified by the series of cuts and pastes needed to construct them, which gives the really counterintuitive implication that compared to dimensions 3 and 4, high-dimensional topology is actually really easy, and it provides a really clear delineation between the fields of low and high-dimensional topology. So maybe if you wanted, you could argue that it's because of cobordisms that so many topologists these days are low-dimensional topologists. And that is the deal of cobordisms.